Ladies and gentlemen, thank you for joining today's lecture on one of the most ambitious robotics projects in recent years, Tesla's Optimus. My goal in the next 10 minutes is to take you on a deep dive into what Optimus is, how close we are to full functionality, what humans still remain involved, and how it stacks up against other humanoid robots currently in development. To begin, what is Optimus? Tesla introduced the concept of a general-purpose humanoid robot capable of performing tasks that are unsafe, repetitive, or boring for humans. The idea is that just as Tesla vehicles moved from wheels to software, now they are moving into the world of walking machines. Optimus is designed to walk on two legs, use two arms and hands, perceive and navigate its environment, and carry out physical manipulation, all with the goal of one day operating in factories, warehouses, and possibly even homes. According to various sources, Optimus stands approximately 5 feet 8 inches tall, weighs around 160 pounds, and is built to carry loads such as roughly 45 pounds, and lift up to 150 pounds in some designs. The company has described it as the same stack of AI that powers Tesla's vehicle autopilot used to drive cars but reoriented for walking and manipulating objects. Now let's look at the key capabilities of Optimus as we know them today. First, locomotion and mobility. Optimus has demonstrated walking, balancing, and in some demos even squatting and doing more dynamic motions such as dancing, or what appears to be light gymnastics. According to reports, Generation 2 of Optimus boasts a walking speed improved by as much as 30% over earlier demos, fluid squatting, and delicate manipulation, including the ability to pick up an egg without cracking it. Next, perception and autonomy. Optimus uses vision systems, sensors, and AI planning models inherited from Tesla's vehicle technology to navigate indoor and outdoor environments, locate and identify objects, and plan its own movements. In addition, Tesla positions Optimus as a platform for repetitive work in factories, for example, walking heavy items, doing pick-and-place tasks, handling logistics, and freeing humans from tasks that are dull or unsafe. On the hardware side, Tesla emphasizes leveraging its expertise in powertrain, motors, actuator design, sensor fusion, and autopilot AI to give Optimus high-torque density actuators, sophisticated control, balance, and the ability to integrate into the industrial infrastructure. In terms of release timeline, Tesla has indicated that limited production of Optimus may begin in 2025, with larger-scale production potentially in 2026. Pricing estimates that have circulated suggest a target price of around US $30,000 for a consumer version, though that number is speculative and depends on volume and capability. It's important, however, to talk candidly about where Optimus still faces significant challenges and where human involvement remains essential. First, even though demonstrations show motion and mobility, many tasks in real-world environments remain extremely difficult. Manipulation of widely varied objects, robust perception under all lighting and clutter, safe interaction with humans, adapting to new environments, and operating reliably outside the lab. Many observers note that some demos of Optimus still rely on human teleoperation or supervised control behind the scenes. That means humans are still involved in calibration, supervision, training, remote operation of tricky cases, and defining tasks and modules for the robot. Humans will remain in the loop for quite some time, defining objectives, setting boundaries, debugging failures, and making strategic decisions. Secondly, safety and trust are major human considerations. Deploying humanoid robots among humans in unpredictable settings demands rigorous testing, auditing, ethical governance, fail-safe fallback, and clear human oversight. Humans must manage deployment protocols, monitor robot behavior, handle exceptions, and maintain responsibility. Finally, human-robot collaboration is a core part of the vision. Optimus is designed not to replace all humans, but to work alongside them, pick up the slack in repetitive or dangerous work, and free humans for higher-value tasks. The human element remains indispensable. Now let's shift to a comparative section. How does Optimus compare with two other notable humanoid robots? The 1X-NEO, home robot, and Xpeng Iron, commercial humanoid. Starting with 1X-NEO, the 1X-NEO is designed primarily for the home environment. According to its product page, NEO is about 5'6" tall, weighs about 66 pounds, can lift up to 154 pounds, and carry a payload of 55 pounds. It features fine manipulation hands, 22 degrees of freedom per hand, and is built for living spaces, chores, and domestic tasks. In contrast, Optimus is larger, targeted more broadly at industrial and general-purpose tasks, and not yet marketed specifically for the home. Where NEO relies more heavily on human teleoperation or remote guidance in early versions, Optimus is positioned for higher autonomy and mass-scale production, though still in prototype. The price point is also very different. NEO is marketed around US $20,000 for early adopters in a home setting. Next, Xpeng Iron. The Iron robot is built by the Chinese company Xpeng and is designed as a next-generation humanoid for both commercial and service roles. Reports state Iron stands approximately 178 centimeters tall, weighs about 70 kilograms, 154 pounds, features synthetic skin, a highly human-like gait and articulation, and is aimed at high-end humanoid service roles in showrooms, retail, industrial inspection, and more. Compared to Optimus, Iron emphasizes presence, design for public-facing roles, and a strong focus on humanoid aesthetics and articulation. Optimus, by comparison, emphasizes a platform approach, industrial utility, Tesla's automotive-style manufacturing scale, and AI stack. In summary, NEO =sign home, teleoperated learning stage, Iron =sign commercial, design forward, premium service robot, Optimus =sign general purpose, mass scale ambition, leveraging automotive production and autonomy. Each occupies a different niche with varying design goals, timelines, and target markets. Finally, let us consider the broader implications of Optimus. If Tesla succeeds in scaling humanoid robots, this could reshape manufacturing, logistics, service industries, and ultimately the workforce. Ultimately, the vision is not just about a single product, but about a robot that can be manufactured at high volume, operate autonomously across many settings, and dramatically reduce the cost of labor or augment human labor. Tesla's Elon Musk has described Optimus as potentially more significant than the vehicle business in the long run, but success is far from guaranteed. Tremendous engineering, manufacturing, software, perception, autonomy, safety, and business model hurdles remain. For end users and industries, the question is not only what can this robot do now, but when will it reliably do useful work in real environments at acceptable cost and risk? In the meantime, human participation, oversight, and collaboration will remain foundational to adoption, deployment, and trust. In conclusion, Tesla's Optimus robot presents a bold vision of humanoid robotics at scale. We have seen significant strides in demonstration, mobility, manipulation, and ambition. But we must remain grounded about the challenges, the human role, and the competitive landscape, especially when comparing with other robots like the one XNEO and Xpeng Iron. If you are in technology, manufacturing, service design, or automation, Optimus is a robot to watch very closely over the coming years. Thank you for your attention, and if you value this content, please like, subscribe, and share.